Hey guys, in our previous video we've developed an equation for the thermal conductivity, for the interface thermal conductivity, and we've actually related it with the general nodal equation. But if you want a significant term through which we can actually find the thermal conductivity at the faces, we have other developed equations apart from this which are easy to calculate. So before formulating the equations, we go on two observations or two assumptions, wherein in the first case we check if the temperature difference or the thermal conductivity difference is slightly different based on the grid points, or is it significantly different. So in the first case, we consider there's a slight variation of thermal conductivity between the grid points. Now, the thermal conductivity at this phase is what we have to determine based upon the thermal conductivities given at these two grid points. If the thermal conductivity at these two grid points is pretty similar or pretty close, then we go ahead with this approach. In the first approach, we write thermal conductivity as a function of the nodal points. I mean, not exactly the nodal points, but a function of the distance and the thermal conductivities of each of the grid points. Like, for example, if I have to determine the thermal conductivity of this phase, I can write my expression of the thermal conductivity as this phase as a function of distance and the thermal conductivities of these grid points in individual. So I'd be writing my thermal conductivity at this phase Ke as Fe times Kp plus 1 minus Fe times Ke. Now you all might be wondering what Fe is. Fe is nothing but the interpolation factor. Now Fe, like as I told you, this thermal conductivity equation is a function of distance as well as thermal conductivities, right? So the function of distance is nothing but the interpolation factor, wherein I would be dividing my thickness. Let's say the thickness between P to E is delta XE, and now the distance from the face E to this grid point E, I would be taking it as delta XE positive, and the distance between point P to this face, I would be taking it as delta XE negative. So the ratio of delta XE positive to the actual thickness is nothing but my interpolation factor. So after theoretical calculations, they've established an equation where the thermal conductivity of a phase is given by this formula. Alright, now for assumptions, let's assume Fe, the interpolation factor, as 1 by 2. So that is, the distance is exactly half. Okay, E is exactly acting at the midpoint, wherein, so if I substitute 1 by 2, I would be getting my thermal conductivity at this phase as the average, the arithmetic mean. So this is applied only when there is slight variation in thermal conductivity. So this would be my equation. But in case of significant variation, I just can't consider the arithmetic mean, because let's say if this is the thermal conductivity in this phase and this is the thermal conductivity in this phase, the average would giving me an aggregate somewhere this midpoint or the line what I've marked in here, which is actually not necessary. So we use a different approach again. So all of us know that Q can be written as K dt by dx. Now in 1D steady state analysis, I would be elaborating my thickness as I told you by considering thicknesses and thermal conductivities in each phase. Like here I've generally written it as delta XE and KE, but when I talk about 1D steady state analysis, I write it as delta XE minus by KP and delta XE plus by KE. So this is what I write. So when I compare these two equations, I can write delta XE by KE is nothing but this term, right? Delta XE negative by Kp plus delta XE positive by Ke. I divide both sides by delta XE and I'm left with my interpolation factors again. So as I told you, delta XE minus by delta X would be 1 minus Fe, and delta XE plus by delta X would be Fe. Now when I plug in 1 by 2 for Fe, that is E is exactly at the center point, I would be getting my thermal conductivity as a harmonic mean. So we use a harmonic mean formula when there is significant difference between the thermal conductivities, and we use the arithmetic mean when there is not much significant variation in the thermal conductivities. So this is how you find the thermal conductivity at a wall or an interface. Thank you.